In the last video, we established when we had Z mod n, when n is not prime, what conditions that we need to hold true such that if I have an element inside of that set, when does it have a multiplicative inverse? And it's true whenever that element, or the GCD of that element n, the modulo that we're dealing with, whatever n, has a GCD of 1. So that's the only case when this is going to work. So in this example here, we want to determine if 62 has a multiplicative inverse in modulo 626. So if we didn't have that last theorem, well, what would we need to do? Well, again, this is in mod 626. So the elements inside of 626 are 0, 1, 2, all the way up to 625. So I'd have to take each one of those, multiply it by 62, and then determine if the congruence class that we end up with is 1. Now, we don't have to do that because we have the last theorem. So let's play around with this one. So back to the workbook we go. We have exercise 6. So we're asking the question, if 62 times some x, where x is in Z mod 626, is equal to 1. Again, mod 626. And again, we can solve this. We can answer yes or no. We're not going to be able to say what the element is, but we can answer right away by determining what the GCD between the two of them is. So 62, 626. The question is, does this equal 1? So is the only thing that divides these two things 1? Well, hopefully right away you can see that the answer to that is not 1. First and foremost, 62 is even, 626 is even, so at the very least, 2 is going to divide both of them. Now, is that the greatest common divisor? Not 100% sure. There could be another one in there. But what I would need to do, or what I could do, is going back to the Euclidean algorithm. So we could find through the Euclidean algorithm what the GCD of these two numbers are. So as a quick refresher, let's go through that exercise. Let's suppose I didn't know that it wasn't equal to 1. So I start off with 626 on my left-hand side. This is equal to 62 times some multiple. So how many times does 62 go into 626? Well, it goes 10 times. So 10 times 62 is 620. The remainder is going to be plus 6. So my remainder is not 0. I don't stop. I continue on. So my quotient from the last time, which was 62, now becomes my left-hand side. My remainder now becomes the quotient here, so this is 6. So the question is, how many times does 6 go into 62? Again, that's 10 times. So that gives me 60 plus 2. My remainder is not 0. I continue on. So again, quotient moves to the left-hand side. Remainder moves over here. Now, how many times does 6 go into 2? Well, it goes 3 times with a remainder of 0. I stop here, and 2 is my GCD. So 62, 626 is equal to 2, which is not equal to 1. Therefore, this element does not have a multiplicative inverse. So see, a lot faster than having to go through all 626 elements inside of there to see if one of those, when I multiply the two together, give me 1. In this case, it's telling me that's not going to happen. So in this theorem here, all we're doing is restating the last theorem in terms of defining what this multiplicative inverse is going to be. So an element in Z mod n is called a unit if the equation ax equals 1 has a solution. So in other words, a is a unit if there is another element b in Z mod n, such that when I multiply these two things together, I get a 1. So in that case, we say that b is the inverse of a, but we can also say that a is the inverse of b. So both of these things are in fact units. A is a unit, b is a unit, because they both have inverses in there. So let a and n be integers with n greater than 1. Then a, the congruence class of a, is a unit in Z mod n, and typically I won't say the congruence class, I'll just say a, is a unit in Z mod n if and only if, again, this is the restatement of the theorem last time, if the greatest common divisor between A and N is 1. Just some definitions here for the next two. So a non-zero element A in Z mod n is called a zero divisor if the equation ax equals 0 has a non-zero solution. So that is, if there is a non-zero element C in Zn such that AC is equal to 0. So again, A is not 0, C is not 0. I multiply these two things, I get a 0. That tells me that A is in fact a zero divisor. And again, that also means C is a zero divisor because I can take C and A and then multiply those together, and I'm good to go from there. So as an example of this, let's go back over to the whiteboard here. I don't have an example in the slides, but that's perfectly fine. Let's make this up. Let's look at Z mod 6. So in Z mod 6, I have the elements here. Again, these are all congruence classes, but again, we'll just treat these as the representatives in here. So 0, 1, 2, all the way up to 5. So I'm looking for the non-zero elements inside of here. So if I look at 1, is there anything else that when I multiply 1 by something going to give me a 0? Well, I would have to try this out. So 1 times 1, well, that gives me 1. Well, that's not 0. 1 times 2, that's going to get me 2. That's not 0. 1 times 3, 3, that's not 0. 1 times 4, not 0. Whoops, that's 4. 1 times 5 gives me 5. Again, that's not 0. So 1 doesn't work. Well, what about 2? 2 times 1 gives me 2. That's not going to work. 2 times 2, that gives me a 4. That doesn't work. 2 times 3, well, that gives me a 6, which again is equal to 0 because we're doing this mod 6. And the distance between 0 and 6 is 6 units, therefore it's divisible by 6, so they're in the same congruence class. And I can keep going with this. 2 and 4 gives me 8. Mod 6, this is 2, so that doesn't work out. 2 and 5 give me 10. Mod 6, this gives me 4. So 2 and 3. And again, I continue to do this for all of them, and I can find my zero divisors in here. But right now, 2 and 3 are two non-zero elements that, when multiplied them together, give me, in fact, a 0. Now remember, if this was prime, so if P was prime, this wouldn't happen because the only things that multiply to give me a 0 is if one of them was 0 to begin with. So another definition. So a subset of Z mod n consists of a collection of all residual classes, so all the elements in Z mod n, which have a multiplicative inverse. So this is Zx, or x is the superscript up there, so this is the set of all units. So the set of all invertible elements by multiplication. So we're looking for all A in Z mod n such that there exists a C in Z mod n where AC is equal to 1. So basically, one way to think about this is we can look at all of the elements A in Z mod n such that the GCD between A and n is equal to 1, and then they would be in the set, because every one of those has in fact a multiplicative inverse, and that's just by our theorem and definitions. So let's finish this up with exercise 7. We want to write down all of the elements in Zn star. Sorry, not Zn, Z9 star. There we go. And we're making this a little bit more challenging because in this case, n is in fact not prime. All right, so back over to my whiteboard here. So we're looking to build Z mod n x, which this is going to be made up of all the elements A in Z mod n, such that the GCD of A and n is equal to 1. So all of the elements in A, well, what are the elements inside of here? These are the non-zero elements. So my non-zero elements are 1, 2, 3, all the way up to 8. All right, so if I'm looking at the GCD, again, of A and 9, we're asking the question, well, what is this? First and foremost, well, what divides 9? Because we're looking for the common divisors, the greatest common divisor between them. So what divides 9? Well, 1 divides 9. 2 doesn't divide 9. 3 divides 9. 4 doesn't. 5 doesn't. 6 doesn't. So it's just 1 and 3. All right, so if I look at A, what are my first choices? So I have A is equal to 1. The only thing that divides 1 is 1. So 1 and 9 have a greatest common divisor of 1. So Z mod 9x, first element inside of there is 1. Well, what happens when A is 2? What divides 2? Well, the things that divide 2 are 1 and 2. Well, the only thing between 9 with 1 and 3 is in common of that is 1. So 2 is also in there. What about 3? Well, 3 divides 3. 3 also divides 9, so it's the greatest common divisor. That's not equal to 1, so 3 doesn't work. 4, what divides 4? I have 1, 2, and 4. The only things in common with 9, again, that's the 1 and 3, is 1. So 4 is going to work. 5, only thing that divides 5 is 1 in itself, because 5 is prime, so again, only thing it has in common is the 1. 6, what divides 6? Well, we have 1, we have 2, we have 3. Well, 3 divides 6, 3 also divides 9, so that's my greatest common divisor there. So that doesn't count. I have 7, 7's a prime, so again, that's going to fall into here. And 8, what divides 8? I have 1, 2, 4, and itself. So again, in terms of what it has in common with 9, the only thing it has in common with 9 is 1. So that's going to work. So these are my elements in Znx, which is the set of all units in Z mod n. All right, so that wraps up this lecture. If you have any questions, comments, concerns, please feel free to reach out. We'll see you at the next problem-solving session, or we'll see you in the next video lessons. Till then.